Okay, so ready for section 8.3. So just a note that we're skipping over sections 8.1 and 8.2 in the class. So we want to talk about section 8.3, which is in chapter 8. So chapter 8 is titled Trigonometry Applied to Polar Coordinate Systems and Vectors. Section 8.3 is titled Complex Numbers in Polar Form. Right. So if you took college algebra, you should have talked before about complex numbers. It's currently in our textbook in chapter 1. So I pulled some information just to review in objective 1 about what a complex number is. So just a refresher, a complex number is the following. So given real numbers a and b, a number written in the form a plus bi is called the complex number. The value a is called the real part of the complex number, and the value b is called the imaginary part, right? So here's just a quick example. We have 5 minus 7i, so that's equal to 5 plus negative 7i, right? Because we need to write it in a plus bi format. So the real part in this example is 5, and the imaginary part is negative 7. So just some notes. So if b is 0, then a plus bi equals the real number a, right? And if you don't see that immediately, right? So if we have a plus 0i, right? This part is just 0, so this would just be equal to a plus 0, which equals a. Right, so that's what that's telling us. So this tells us that all real numbers are complex numbers, right? So all real numbers are also complex numbers is what it's saying, right? Because if you have a real number a, then, or if you have a real number, let's say n, then you could just let n equal a and b equal 0, then you have a real number, right? So here's an example. So like the real number 4 plus 0i is a complex number, but typically we write it just as the real number 4, right? And then if a equals 0 and b does not equal 0, then a plus bi equals bi, which we say is pure imaginary, right? So same idea, if I have 0 plus bi, that's just equal to bi, right? So we get this, we get just bi, and we just call that purely imaginary, right? There's no real part to that. So here, the number 0 plus 8i is a pure imaginary number and is generally just written as 8i. Right? So then something else as review is that a complex number written in the form a plus bi is said to be in standard form, where I equals the square root of -1 and I squared equals -1. Right? So again, that was just a quick refresher of what a complex number is. And now we're ready to start discussing objective 1, which is to be able to plot complex numbers in the complex plane. Right? So first of all, let me just define what the complex plane is. So the complex plane is a plane, right? And just maybe just to clarify really quick, right? Like if I talk about like the xy plane, right? That's just a like the xy coordinate system, right? Where this is the x-axis and the y-axis, right? A plane is basically an infinite sheet of paper, right? It's like a two-dimensional thing, right? So the complex plane is a plane with a horizontal axis called the real axis, and a vertical axis called the imaginary axis. A complex number z equals a plus bi is written as an ordered pair a comma b, and can be then be graphed as such in the complex plane. Right? So basically, what I'm trying to say is if we have a complex number, a plus bi, then a is like the x-axis, if you will, the real part, and then b, the imaginary part, we can treat that like the y-axis. Right? And just a kind of a side note is, I wrote z equals a plus bi. So z is often used to represent a complex number by tradition. Right? So let me just draw an image here. So if I have, like a coordinate system, right? Basically, if we want the complex plane, the x-axis, the horizontal axis, is now what we call the real axis, right? So in other words, that's where I'm going to graph the a value. And then the y-axis, the vertical axis, is called the imaginary axis. Right? So it's like the b-axis. Right? And then if I want to graph, the point a plus bi, right? Then let's say, this lines up with a, and this lines up with b. Then this point at a comma b is equivalent to a plus bi, right? That point is graphing a plus bi. Right? So let's practice this. So example 1, we're given some complex numbers and asked to graph those on the complex plane. So first of all, the first thing I would do is just rewrite these as ordered pairs, and you want to make sure that they're in the form a plus bi. Right? So the very first one, since that's a plus, that's in this format, right? So in other words, for this guy, a equals -1 and b equals 3. So this is the point -1 comma 3. Right? This is the same thing as -4 plus -5i. Right? So this tells me that a equals -4 and b equals -5. So that gets mapped to the ordered pair -4 comma -5. Right? So 3 is equal to 3 plus 0 I. Right? So this tells me that a equals 3 and b equals 0. So this becomes the ordered pair 3 comma 0. Right? And then lastly, 4i is equal to 0 plus 4i. So this tells me that a is 0 and b is 4. So this gets mapped to the ordered pair 0 comma 4. Right? So now I just need to create my complex plane. So maybe we'll go up by 5s. We're going up by 1s, but I mean covering values between -5 and 5, right? So then just plotting -1, 3. Whoops, and just to specify that this is my a-axis and this is my b-axis, right? So that tells me I'm in a complex plane, right? So -1, 3 is going to be here. -4, -5, going to be here, and then 3 comma 3 0 is here, and 0 4 is here, right? So this point is -1 plus 3i. Let's see, the point 0 4 was 4i, and this guy was 3. And lastly, this one was -4 minus 5i. Right, so that's where all of those graphs, all those complex numbers would be graphed on the complex plane. Right. So then the next thing that we want to think about is the absolute value of a complex number. So if z equals a plus bi is a complex number, then the absolute value of z, also called the modulus or the magnitude of z, is given by, that we have like the absolute value of z, right, equals the square root of a squared plus b squared, right? So this should look familiar with you. The square root of a squared plus b squared is essentially the distance between a point AB and the origin, right? Because if I have, if I have just a complex plane, right, with the real axis, and my imaginary axis, then if I graph the point AB, right, so maybe, this is A and this is B, so this point is, the ordered pair AB, which is graphing z equals a plus bi, then graphically, if I draw a line segment from the origin to that point, that distance is equal to the magnitude of z. Right? So, if this is the point 0, 0, and that's the point, so that's the point A comma B, right? Then if I, find the distance formula, right? Remember the distance formula is equal to the square root of, x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So the distance formula would be equal to the square root of, so we would have a minus 0 quantity squared plus b minus 0 quantity squared, which, subtracting 0, you just get that value, right? So this would just become the square root of a squared plus b squared, which is exactly what we have, right? So that's what I was meaning by that the distance between the origin and the point is equivalent to the modulus of z, right? So maybe just to write this out, I could say that geometrically, the number, the modulus of z, is the distance between the point AB and the origin. Right, so I think now we're ready to try some examples, right? So if I'm trying to find the modulus in example 2 of part A, we have z equals -5 minus 12i, right? So in other words, the modulus of z is going to be equal to the square root of, and then you take a squared, so -5 squared, plus b squared, which would be -12. Right? So this is equal to the square root of 25, because -5 squared is 25, and then -12 squared is 144, and then 25 plus 144 is 169, and the square root of 169 is equal to 13. Right? So for part A, the modulus of z is 13. And then for B, we have z equals 4 plus 6i. So the modulus of z is going to be equal to the square root of a squared, which would be 4 squared, plus b squared, which is 6, so 6 squared, equals the square root of 16 plus 36. So then 16 plus 36 is 52. Right, so we have the square root of 52. And I can simplify this, right, because 52 is equal to 4 times 13. So I can rewrite this as 4 times 13, and 4 is a perfect square, right? That's why I wrote it in that fashion. So then this just becomes, so using the multiplication property radicals, this would be radical 4 times radical 13, and radical 4 can simplify to be 2, so this equals 2 radical 13, right? So that's the modulus in simplified form. Right. All right, so now that we know, recalling a little bit about what a complex number is and how to plot it, find the modulus, now we're ready to talk about what's called the polar form of a complex number, and that's basically where the trig is going to be coming in. This first part page here, I just have kind of like just some theoretical kind of things and definitions to go through to present some things, and then we'll practice some more examples. So, Z equals A plus BI is in rectangular. Oops, hang on. Or what we call Cartesian form. Right. So a famous mathematician, René Descartes, he's the one that came up with being able to plot points in the coordinate system. So that's why we call that Cartesian, right? If you maybe never heard that before. So we can say let A and B both not be equal to 0, right? Let R represent the length of the line segment between the origin and the point A comma B, right? Where Z equals A plus BI, and of course I equals the square root of -1, right? So in other words, R is going to be equal to the modulus of Z, right? Because pictorially, right, we're saying R is the distance between the origin and AB, and we just had talked about that, right? What that means geometrically. So R is just going to be equal to the modulus of Z, which is equal to the square root of A squared plus B squared. And this is going to be greater than or equal to 0, right? Because it's like a distance, right? So we have that. And then next, let's say let theta be the angle in standard position with terminal side through the point A comma B. Right. So let me draw a picture here. So if I have a complex plane where this is the origin 0, 0. Let's say this point over here is AB. Then what we're saying is drawing a line segment with terminal going through the terminal side, right? Like this here. So this angle is theta. This x coordinate matches up with this point's A, the B value matching up is B. Right, I can draw a dotted line down. It's a right angle then. So that means that this side is B, and this this distance here, from the origin to the this xy a is A, of course, right? And then this guy, the hypotenuse, is going to be equal to R, right? Because that was the modulus of Z. So since we have a right triangle, I could use my my trig, SOHCAHTOA, right? And I could figure out, for example, what sine of theta is, right? So sine of theta is going to be the opposite, which is going to be B, divided by the hypotenuse, which is R. And then if I multiply both sides by R, right, what I'm going to get is R sine theta equals B, right? Because those R's are going to cancel out, right? So in other words, B equals R sine theta. And I'm going to put a box around that because we're going to need that. And then cosine theta is equal to the adjacent, which would be A, over the hypotenuse, which is R. So if I multiply both sides by R, right, that's going to give me, so these R's cancel out, R cosine of theta equals A, right? So in other words, A equals R cosine of theta. Right? And just to specify, I guess I didn't say this, but it goes without saying in this section that this is the real axis and this is the imaginary axis. Right? So then Z is equal to A plus BI, right? But I have some new ways to calculate A and B. So what this would become is R cosine theta plus, so just plugging in that value for A, plus R sine of theta, and that's times I, right? But it might be a little more convenient to maybe write it like this, R cosine theta plus I R sine theta. Right, so we'll just put the I in front here. Right, just makes it look a little better, so I know I is not inside the trig ratio sign. And then now I could pull out an R, factor out an R, so that gives me cosine theta plus I sine theta. Right? So this guy, so this is called the polar form, or a trigonometric form of a complex number. Right, so if we refer to the trigonometric form or the polar form, we want to rewrite Z like this. Oops. And that's what I have here at the bottom, right? So the polar form, a trigonometric form of a complex number. Oops, I forgot some letters in trigonometric. Of a complex number, Z equals A plus BI, is Z equals R times cosine theta plus I sine theta, where A equals R cosine theta, B equals R sine theta, R equals the square root of A squared plus B squared, and tangent of theta equals B divided by A, where A cannot be equal to 0. The value of R is the modulus of Z, and we say that theta is an arrangement, an argument of Z. There are infinite many choices for theta, but normally theta is taken on the interval, between 0 and 2 pi, or between 0 and 360 degrees. Right, so just within one revolution. Right. So now we're ready to work with some of these. Let's try some examples, practice this. So example 3, we want to write the complex number but in polar form. So we're given z equals 1 minus I, right? And just to make that clear, that's equal to 1 plus -1 times I, right? So just to make that a little more obvious. So that tells me that A equals 1 and B equals -1, right? So I'm going to need to know R. So R is equal to the modulus of z, which is equal to the square root of a squared plus b squared. So this would be the square root of, so a is 1, so that would be 1 squared, plus b is -1, quantity squared, equals, and then this would be the square root of 1 plus 1, right? Because 1 squared and -1 squared are both 1. So then this would equal the square root of 2, right? So then, so I know what R is. So R is radical 2. What's left is I need to know what theta equals. So what I would do is plot the point AB, right? So in other words, 1, -1. And you can see that that point is in the 4th quadrant, right? So there is theta, right? And then this part in green, maybe I'll call that alpha, right? That's the reference angle for theta. So basically what we have, if we pull that out, is a triangle that looks like this, where this is 1 and this is 1, and I'll just write the absolute, just write the distance, right? And then so if this is a special right triangle, right? This is this would be radical 2, right? Where this value is pi over 4. Right? So and you could find, you could find the square root of 2 by using Pythagorean theorem as well, right? So a squared plus b squared equals c squared, right? So what we'd have is 1 squared plus 1 squared equals c squared. You could figure that out, right? But also, we know that that distance is equal to r, so that's another way you can find radical 2, right? So since it's that special right triangle, I know that reference angle is pi over 4, but if you didn't recognize that, you could use one of the trig ratios like cosine or tangent to figure that out. So then theta is going to be equal to 2 pi minus pi over 4, right? Because we're just short pi over 4 from being 1 revolution. So then I need to get common denominators, so that would be 8 pi over 4 minus pi over 4, which is 7 pi over 4. Right? So z is equal to r times cosine theta plus I sine theta. So z is going to be equal to, so just plugging in what we know, so this is 7 pi over 4, right? So I would have radical 2 times cosine of 7 pi over 4 plus I times sine of 7 pi over 4. Right? Alright, so then part B, we have z equals 3 plus 4i. Right, so this one, you can kind of clearly see that a is 3 and b is 4. So might start out by finding the finding r, which is the modulus of z. So this would be equal to the square root of 3 squared plus 4 squared, which equals the square root of 9 plus 16, which equals the square root of 25, which equals 5. Right? So if I plot the point 3, 4, here we get this. So if I draw in the right triangle, I know this is 4, that's 3, and we just found that that's 5, right? So in other words, to find the angle, so I want to know this angle theta. So I could say that tangent of theta is equal to the opposite over the adjacent, so 4/3. So that tells me that the inverse of tangent of 4/3 is equal to theta. So we know that z equals r times cosine theta plus I sine theta. So then z would be equal to 5 times cosine of inverse tan of 4/3 plus I times sine of inverse tan of 4/3. Right, so there we have it in polar form. Right. So now, example 4, we're kind of working backwards. We have, at least working backwards from what we just did. So we have a complex number written in trig form, and we want to write it in rectangular form, right? So in other words, remember, I want to write it as a plus bi, right? So it's important to note that r is 6 here, and theta is 150 degrees, right? So just pulling those parts out of that form. And then remember that we want to find a and b, right? So I might start by just maybe plotting a comma b, right, or what we think it would look like. So in other words, we have this line segment, and this angle is 150 degrees, and then this distance of this line segment is 6, right? And then this would line up to A, and this would line up to B, and we want to find what those values are. So A is equal to r cosine of theta, right, that we talked about before. Excuse me. So just plugging those values in, r is 6, and then we'd have cosine of 150 degrees, which equals, so then, remember, all students take calculus, and what we have is this situation where this would be 30 degrees, right? So that's 60 degrees. So this would be, radical 3 over 2, and this would be 1/2, and this is 1. Right, so cosine is negative in the second quadrant. So this would be 6 times negative 1, and then cosine of 30 degrees would be radical 3 over 2. Right? And then b is equal to r sine theta, which equals 6 times sine of 150 degrees. And sine is positive in the second quadrant, so this would be 6 times sine of 30 degrees, which is 1/2. Right? It looks like I didn't simplify these. Sorry. So a, if I simplify this would be, so 6 divided by 2 is 3, so this would be negative 3 radical 3. And then this guy would just be 3. So then z equals a plus bi, which would be equal to negative 3 radical 3 plus 3i. Right, so just plugging in those values for a and b. So z equals negative 3 radical 3 plus 3i is what we were after. All right, so in chapter 1, if you took college algebra, you learned how to add, subtract, multiply, and divide complex numbers in rectangular form. So what we want to focus on now in this section is how do we multiply and divide complex numbers in polar form. So I have this box taken from the textbook that just shows, if you have z1 equals r1 times cosine of theta 1 plus I sine of theta 1, and z squared equals r squared cosine theta 2 plus I sine theta 2, then we have the product and quotient formulas, right? So I just want to present how to come up with the equation 1, the product of complex number in polar form, and then I'll post a video of the quotient form in case you're interested, right? So let's let z1 equal r1 times cosine theta. Oops, that didn't look too good. Plus I theta 1 times I sine of theta 1, and z2 equals r2 times cosine theta 2 plus I sine theta 2. Right, so then if we just write this, z1 times z2, right, we're trying to find the product of these two complex numbers, that would just be equal to r1 cosine of theta 1 plus I sine of theta 1 times r2 cosine of theta 2 plus I sine of theta 2. Right? So this would just be equal to, so r1 times r2 times cosine of theta 1 plus I sine of theta 1 times cosine of theta 2 plus I sine of theta 2. Excuse me. Right, so we can just use properties of multiplication to rewrite that, right, using the associative and commutative properties of multiplication. So then what we would have next is we need to FOIL these two parts, right, in parentheses. So this would be r1 times r2, and then we'd have times cosine theta 1 cosine theta 2 plus I cosine theta 1 sine theta 2 plus I sine theta 1 cosine theta 2 plus, and then lastly we would have I times I squared times sine theta 1 sine theta 2. Right. So, and just a note that this guy, I squared, is equal to -1. Right? So this would become r1 times r2 and then what I could do is write the things without an I first, and then the things with an I next. Right? So cosine theta 1 cosine theta 2 do not have an I, and then this last term isn't going to have an I because I squared is -1. So this would be, minus sine theta 1 sine theta 2. And then I would have plus, and then I have these two terms, and what I could do is factor out an I, so that would be I times cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. And then now I'm going to continue on the next page. So I'm just going to say, let this equal star, and then I'll just continue this on the next page. And then what we're going to have to use are the sum formulas for both cosine and sine that was presented in section 6.2 to rewrite the following, right? So what you're able to recognize is that this part is simply just cosine of theta 1 plus theta 2. And this guy is just sine of theta 1 plus theta 2. Right, using those sum formulas from section 6.2. So then what we can get is that this is going to be equal to R1 times R2 times cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. Right, which is equation 1. Right, that's what we were trying to show. Right. So then, like I said, if you want to see 2, check out the video. Right, on Carmen if you're interested. Right. So then, ready to go to the next page. So the next page we're looking at example 5. So of course we're going to practice, multiplying and dividing these equations in polar form. And then the next page we have one last objective to cover, right? In the textbook, just to note this, the textbook section actually has 5 objectives, but the 5th objective is not going to be in this class, right? For time's sake, and this not typically in the class anyway. So example 5, we have Z1 and Z2, and we're asked to find the product of both of them and write it in polar form, right? So the first thing that I kind of like to do is just label everything, right? So looking at Z1, that 3 is equal to R1. So R1 equals 3, and theta 1 equals pi over 12. And then if we look at Z2, we know that we can see that R2 equals 2, and theta 2 equals pi over 6. Right, so it's just a matter of plugging things in, right? We know that Z1 times Z2 equals R1 R2 times cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. Right, that's just the equation presented on the previous page. I guess two pages, right? So then if we just plug these values in, we would have 3 times 2 times cosine of pi over 12 plus pi over 6 plus I sine of pi over 12 plus pi over 6. Right? We might just come off to the side, right? Pi over 12 plus 2 pi over 6 would be 2 pi over 12, which that's just 3 pi over 12, which that reduces down to be pi over 4, right? So just doing that simple arithmetic there. So this becomes 6, right? 3 times 2 is 6 times cosine of pi over 4 plus I times sine of pi over 4. Right? So that's the answer that we're after, right? So that's the product in polar form. So then we can do the same thing here. So looking at this, we're doing a quotient this time, right? So R1 is 18, and theta 1 is equal to 75 degrees. And then here, R2 is equal to 2, and theta 2 is equal to 255 degrees. So we want to be able to find that, right? So the equation is Z1 divided by C2 is equal to R1 divided by R2, and that's times cosine of theta 1 minus theta 2 plus I times sine of theta 1 minus theta 2 right, where of course Z2 cannot be equal to 0, so, which is not the case, right? So then Z1 divided by C2, if we just plug these values in, we would have 18 divided by 2 times cosine of 75 degrees minus 255 degrees plus I times sine of 75 degrees minus 255 degrees, which is equal to 9. 18 divided by 2 is 9. And then 75 minus 255 is 180. So this would be cosine of negative 180 degrees plus I sine of negative 180 degrees, which is equal to 9 times cosine of, so it's important to note that negative 180 degrees is coterminal with 180 degrees, right? So if I add 360 degrees to it, I get 180. So this would be the same thing as if I wrote 9 times cosine of 180 degrees plus I times sine of 180 degrees. Okay, so just as I mentioned before, when we talked about polar form, we typically write theta in between, like 0 and 2 pi or 0 and 360 degrees. Right? So that's the quotient. Right? So then objective 4, we're going to be able to compute powers of complex numbers using a theorem. Right? So the theorem is if z equals r cosine theta plus I sine theta, so in other words, z is in polar form, and n is a positive integer, then the following equation is true. Right? And you can read over that, and you might kind of wonder, how does that exactly come from? And so I'm going to post a proof to this on Carmen as well, if you're interested. But the basic idea is if you let z equal r times cosine theta plus I sine theta, then you can begin to take, square z, right, which that's just going to be equal to z times z, so we would have r times cosine theta plus I sine theta times r cosine theta plus I sine theta. So r times r is r squared, right? And then when you FOIL these two things, it turns out that that's just going to equal cosine of 2 theta plus I sine of 2 theta. So how you get that is once you FOIL those out, you're going to have to use the double angle formula that we talked about in chapter 6 as well. And you can simplify it to that, right? So then you could calculate like z cubed, right? So that's going to be, z squared times z. So you're just going to take your previous answer, r squared times cosine of 2 theta plus I sine of 2 theta, and then multiply that times r cosine theta plus I sine theta. And then when you multiply that out, that turns out that that's going to become r cubed times cosine of 3 theta plus I sine of 3 theta. Right? So you can keep doing this, and you kind of see this pattern emerge. Right? So that's not necessarily it may be a proof necessarily, but just to get you thinking about that. Right? So let's practice some examples of this, and then we'll call it a day. This video's getting long enough, I think. So we have two examples. So example 7 is we want to compute 4 times cosine of 70 degrees plus I sine of 70 degrees cubed, and we want to write it in the rectangular form. So I can apply the theorem that we just talked about directly because it's already in the complex numbers already in the trig form. So 4 times cosine of 70 degrees plus I sine of 70 degrees. If I cube that, that's equal to, right, so just using that formula above, right, we're just going to take the r value, which is 4, raised to the n power, which is 3, Right, so in other words, this is r, this is theta, and n is 3. Right, r is 4, theta is 70 degrees. So we'd have 4 cubed times cosine of 3 times 70 degrees plus I times sine of 3 times 70 degrees. Right? So 4 cubed is 64, so this gives me 64 times cosine. So 3 times 70 is 210 degrees. And then plus I times sine of 210 degrees. So then how we can put this into rectangular form is actually to evaluate cosine of 210 degrees and sine of 210 degrees and just plug that value in, and then we can simplify as much as possible. So to be able to do that, let's just draw the coordinate system. Right, so 210 degrees is going to be here. Right, and all students take calculus, right? So with 210 degrees, this part is going to be 30 degrees, right? So if I draw, kind of just take this triangle out of the coordinate system and just draw my special right triangle. This would be 1/2. This side is radical 3 over 2, and this is 1. So cosine of 210 degrees is equal to, and then we know we can get sine of 210 degrees is equal to. So in the third quadrant, the only thing that's positive is tangent and cotangent. So both of these are going to be negative, right? So then cosine of 30 degrees is radical 3 over 2, and sine of 30 degrees is 1/2. Right, so that means cosine of 210 is negative radical 3 over 2, and sine of 210 is negative 1/2. So then I can plug those in, and we get 64 times, so this would be negative radical 3 over 2 plus I times negative 1/2. So if I distribute the 64 through, this first part becomes negative radical 3, negative 32 radical 3, and then minus 32i. Right? So again, just taking that 64, multiplying it through. So 64 divided by 2 is 32, right? That's where that comes from. Right, so that is my answer in rectangular form. So now we're ready for the last example. So the only difference for this one is that my complex number is already in rectangular form rather than it being in trigonometric form. So in taking negative 2 minus ti and multiplying that together 4 times, that can be kind of tedious. So if we use trig a little bit, we can make that a little easier, right? So first we could put it in polar form and then apply the de Moivre's theorem. So z equals negative 2i minus 2i, which is equal to negative 2 plus negative 2i, which that gives me that a is negative 2 and b is also negative 2. Right, so r is going to be equal to the modulus of z, which equals the square root of negative 2 squared plus negative 2 squared, which equals the square root of 4 plus 4, which equals the square root of 8, right? And that will actually simplify because I could rewrite that as 2 radical 2, but I'm going to leave it as radical 8 for now, and it'll might be a little easier to work with, and it will. So then what's left is we need to calculate theta. So if I draw just a complex plane and plot the point negative 2, negative 2, Right, we get a point here in the third quadrant. I know the r value is radical 8, and what I'm after is what's theta. Right? So if I pull this apart, this triangle, this is what we get. So this is this would be 2, 2, and remember radical 8, that's the same thing as radical 4 times radical 2, which is 2 radical 2. So this would be 2 radical 2, right? So then if I divide everything by 2, that would give me 1, 1 radical 2, right? So that should be familiar, right? That's one of the special right triangles that we've been working with, and that's when these are 45 degrees, right? So so since I know those are 45 degrees, theta is going to be equal to 180 degrees plus 45 degrees, right? Because this part here is 45 degrees. So then that would equal 225 degrees, right? So that, now that I know theta and I know r, I can know z in the polar form. So z, which is equal to negative 2 minus 2i, is equivalent to radical 8 times cosine of 225 degrees plus I times sine of 225 degrees. Oops, not showing up. Right? So then z to the fourth is equal to, so just using that formula in the theorem, this would be the square root of 8 quantity raised to the fourth power times cosine of 4 times 225 degrees plus I times sine of 4 times 225 degrees. And this would be equal to, so this would be the same thing as like radical 8 squared quantity squared, right? Because 4 is 2 times 2, and we can use the power to a power exponent rule, right? And then this would be times cosine of, so 4 times 225 is 900 degrees. So plus I times sine of 900 degrees. And then 900 degrees is coterminal with 180 degrees, right? So we can subtract 180 until we get a value, or excuse me, subtract 360 degrees until we get a value that's in between 0 and 360, right? So this would be equal to, so the square root of 8 squared is just 8, so this would be equal to 8 squared times, and then this would be the same thing as cosine of 180 degrees, right? Again, it's because these are coterminal, right? Plus I times sine of 180 degrees. So then 8 squared is 64, and then, you know, cosine of 180 is negative 1, right? And again, if you forget really quick, you could just draw a unit circle. Here's 180 degrees, so we're considering this point here. That ordered pair is negative 1 comma 0, and cosine is the x, and the y coordinate is sine. Right, so that would be 64 times negative 1 plus I times 0. So of course, you know, I times 0 is just 0, so this would be equal to 64 times negative 1, which is negative 64. Right? All right, so that's that section. So, you know, don't forget, if you have questions, make sure you're getting a hold of me, and I'll be glad to help. Thanks.